what we will do today would be, I need to make a couple of announcements today. So we have graded the homework 1. So hopefully you can see your grades. Has anybody checked that the grades are up for homework 1?
Yes, sir, they are visible.
That's what I want to check. The second announcement is what we want is we want to have a quiz on Thursday. So for that, you will have to figure something out. What I will do is I will upload the quiz at 1:30 p.m. sharp on Moodle. You download it and upload it back at before 3:30. So you'll have 2-hour window from downloading to uploading, and you work on it. My only request would be that make sure that it is your work and don't waste time in chatting with other folks. It will be based on homework 1 and homework 2. Since both homework and homework 2 has been submitted, we will make a quiz which comprises of both homework 1 and homework 2. Right? Any questions on that one? So that would be, yeah, go ahead.
So fatigue won't be there, right?
Will not be there yet. Yes, fatigue has not been. We have not given any homework. We have not covered it completely. So fatigue will only have quizzes where homeworks have been already given. So and it will be very similar to what we gave in homework. So if you have done your homework independently, you should not have any problems in the quizzes also. Okay. So it will be very similar to what we give in homework. Any other questions? Okay. If not, what I will do is I'll start with today's class. So basically,
hello.
Yeah,
Sir, I missed some part about the quiz because I had a bad connection. Can you please repeat the date?
We will have a quiz on Thursday from 1:30 p.m. the same class time. But what I will do is I will upload the quiz on Moodle before 1:30 p.m. So you should be able to access the quiz at 1:30 p.m. Download it, and then you upload it back before 3 p.m. Okay, as you do your homework. So you have to work for 2 hours and upload it back to within 2 hours. So you have to download and upload the entire your work. Okay.
Okay, thank you.
And if there are any issues, shoot an email immediately. Don't wait after that. So if there are any issues, connection issues, power outage, all you do is just send me either an email or a post. So there should be an official record that you had issues. Okay, you cannot cry post facto that okay so whenever there is a problem, at that very moment you raise an alarm. Okay, shoot me an email and post also on Teams. Both the things you should do. Okay, and if there is no internet, then what I will do is your phone is still on, right? So I'll give you my I'll give you my number also. You can text me. That's the last resort, right? Just SMS me. Don't call me. Okay. So I'll give that also. So that's the final resort. If you have no internet, no power, I'm assuming phone would still be working. Okay. So that is what we will do. Right. So let's now start the class. So we were here. Let me just go ahead and do this. So what we did was we were doing some fatigue modeling, and this fatigue modeling was primarily empirical modeling of the form of SF dash is equal to A and N is life cycle raised to B. So that is what it is. And we can use the same formulation for fully reversible stresses for finite life prediction. Right, what will be the finite life if there is a fully reversible loading sigma? And the SN diagrams which we have discussed up till now are only applicable for completely reversed stresses. And then there is something called low cycle fatigue, which is defined between 1 to 10,000. And here, typically, the failure is primarily by yielding. So yielding will occur first before fracture. So typically there is some yielding involved in that domain. Okay, but then the sun diagrams can also find out the low cycle fatigue. So there are three things which I talked about. There is low cycle fatigue right here. There is finite life prediction, and then there is infinite life. So anything above 10 to the power 6 cycles is infinite life. That's what we design for. Most of the products are designed for infinite life, meaning for more than 1,000,000 cycles of operation. Okay, and this is what you have to. This is how you basically find out your components B, A, and N. So what we will do is we'll do a small problem. And before I do that, what I will do is I will do a couple of things. I'll show you the problem, and then let me open the book because you need some information from the book also. So the question says, let me just read out the question for you and then we'll do something. The question says that I have 1050 hot rolled steel. Everybody knows what 1050, sorry, what is 1050 hot rolled steel? Who doesn't know what 1050 hot rolled steel means? So 1050 hot rolled steel. Any suggestions? You can type in the chat box or unmute yourself and talk to me. What is 1050 hot rolled steel? Hot rolled, you understand, it's hot rolling process by which the steel has been made. But what is 1050? What does 1050 mean? Okay. So 1050 basically tells you carbon content of steel. So 50 is 0.5% carbon. Okay. So that's what 1050 means. So what I will do is I will look at the property. This property is given in table A20. Let me just go ahead and show you where A20 is in Shigley's book. I would want you to read the Shigley's book because you will have to use a lot of information from here. A is appendix. Let's go into the appendix first. Yeah. Appendix. Let us go into appendix. It should be right in the end. A20, table A20, these are all figures, table A20, table A13, A14, table A20. A17, A18, A19, and A20. Right here, it's A20, right? So the AIC grade, if you see, is 1050 hot rolled. So 1050 hot rolled is this one, if you can see. This is, so it has 90 psi is 90 psi is its tensile strength, ultimate tensile. UTS is 90 psi, and its yield strength is 49.5. And these are some of the data for that. Okay, so basically, let's go and see now here. I have 1050 hot rolled steel. So I looked at the properties, and all these properties are tabulated in the book here. So you'll have to learn to get this data. And this data shows that my ultimate tensile strength for this material is 90 kpsi. And typically what happens is SE dash is the endurance strength for fully reverse cycle. The idealized, this is the idealized thing with rotating test, whatever you do. Your RR mode tests, if you do, you'll get this value. So let me just show you. So basically what happens in most of the carbon steel, if you see carbon steels, I can use SE dash by SUT 0.5 right here in the center line. So my I know for sure that my endurance is 0.5 roughly, give or take, of 90, which is 45 kpsi. So I have both data. I have the ideal endurance limit for this SE dash, which is 45 kpsi, and I have SUT 90 kpsi. now I have to find out what will be the empirical equation for its life. So let me just go and show you what these things are. I have a Mathematica thing worked out, so I'll just show you in Mathematica. So this is what it looks like. So I know SUT, I know SC is 45, I know F is 0.86. Now how do I find F? Let me show you. So this is, again, you can look at it. So I know my SUT is right here 90. If you will see, for it's your F, so this SF dash is equal to FSUT, right? If you remember that, that's for finite life. So your finite life thing is a function. You need to find something called F. So here what happens is, here the drop in the low cycle fatigue, which is basically at n is equal to 10 to the power 3, your fatigue strength, your fatigue limit basically becomes a fraction of ultimate strength, and this fraction can be looked up from this chart right here, from this chart. So this F is a function of what is my ultimate strength. The higher the ultimate strength, the lower is the lower fraction is what you get of F is lower as you go, as the ultimate strength becomes higher and higher. So basically, if I am at 90, it's 0.86. The fraction is 0.86. So this is what I did. I found out F is equal to 0.86. F is equal to 0.86. F is equal to 0.86. And I have to find out what will be the empirical relation, which basically says A n, which is number of cycles, raised to b. So b, if you remember, is given by -1/3 log FSUT by SE. Let me just go ahead and show you where we derived this. This is where we derived this. This is where we derived this. Just one step. Just 1 second. I think you'll see it in a bit. The response time of the screen is a bit slow, so you should see it in a bit. Yes, right now you see. So this is B right here. This is B. This is A. So these, if I know this, I can find out this relationship, SFA to the power NB. This is what I do here. So this is what I do here. I go ahead and find out what is my B. So basically, let me just do this. So I can find my B from this equation. SUT is 90. I do the thing. So, oh, sorry, my mistake. I haven't run this cell. So let me run this cell and then I do this. So B turns out to be -0.078. And A, I'll go ahead and find A also. A turns out to be 133.218. So B and A are there. So now I have the equation here, A n to the power B. So let me just go ahead and show you this. Okay. I had found, so this is it. If you remember this, I found out that the equation of the life is SF dash is A, which is 133.1, N is the life, and B is 0.0785. That's a very simple formulation. But remember, these are only true for ideal conditions. So if there is a design which is not ideal, you will have to figure it out, right? A rotating beam, I can find out this all is true only for rotating beam test, RR Moore kind of a test. It's not true for a functional product. So today we'll discuss how do we implement this information for real life products. Okay. I'm seeing some complaints about people not being able to see the shared screen. Can somebody unmute and say that if they're not able to see the screens?
I can see the screen, sir.
Yeah.
Anyone else can confirm it?
There are a couple of people who think that I'm not able to see the screen.
Hello, sir.
Yeah.
So you might try like resharing it, like stop the sharing and then reshare. So that might solve the problem.
No, because I can see it. I have two computers. I can see my own screen. So I'm signed from two accounts, and Chaitanya can also see it.
Yeah,
So
sometimes if you are unable to see, I think so you should leave and come back.
Yeah, I've already tried that.
Okay,
Oh,
let me reshare it if it works. but I can see it because I am on two computers. I can see my shared screen.
Yes, sir. Sometimes there might be a glitch, sir. If you just like stop the share and then restart it, then the person who like joined a bit late, they could be able to see after that.
Okay, let me do this. Okay.
Yes, sir. It is visible now. Thank you.
Okay. So this is what I wanted to show, that these conditions are ideal. Now, if I want to find out, this is the equation of life cycle. SF dash is equal to A and B. If I know that I am subjecting this rotating beam only to 55 ksi, what will be the life of this? I want to find this out. So now I have the equation, so I can plug SF dash as sigma reversible, and then find out what will be the n, what will be the life cycle. That's all I got to do. Let me just show you again with my Mathematica, and you'll get it. So basically, I know that my sigma rev is 55. So I can go ahead and find out what will be the finite life for it based on that equation. So my finite life, if you see, comes out to be 77,614 cycles. Something like something similar what they are getting, 77,500. Okay. Right. So I'll now. So any questions here? So this is only for ideal. So it's only for ideal for ideal conditions. Now, if the conditions are not ideal, we'll discuss that. So before we start non-ideal conditions, I would like you to ask if you have any questions on whatever we have discussed up till now. And meanwhile, what I will do is I'll reshare the other computer. I'm not using Mathematica anymore. So what I will do is I'll stop sharing this and share the other computer. Okay. Yeah. So talk to me if you have any questions.
So could you just tell once what that 55 psi was in the third part?
Okay. Just 1 second, let me get there. Okay. Okay. So what I was saying is, I have this equation now, right? SF dash is equal to A n to the power B. Now this I have find out from my rotating beam test. I actually did a rotating beam test and I found this out. So I know that this is the relationship. So I found out A and B, right? Because I know SUT, I know F, so I can find out A and B. So I have this relationship for any finite life. Now, if I am loading only 55 KSI, right? KSI, right? Yeah, 55 KSI, KPSI, sorry. 55 KPSI. 55 KPSI. In this case, I need to find out what would be the life of this. So I have this equation. So all I have to do is I do 55 is equal to A and B is for a given material, whatever material I'm using. So I can do A to the power N to the power B. And I know A and B, right? So I can solve for N. This is what I did. But the only thing you have to note here is that this is valid only for ideal conditions for rotating tests. So this life which we have found out, that 77,500 cycles, is true only for rotating beam test. Rotating beam test. Now for a real condition, this is what we will discuss now. Any questions now? Did you understand what I'm trying to say? So I have found out the equation for the life, for the fatigue life, and I can find out for a different loading condition what will be the fatigue life from that equation. So if I load for 55 kpsi, this will last 77,500 cycles. But if I load 45 kpsi, it will last How many cycles? 1 million cycles. Right? Did I explain what you had issues with?
Yes, sir. Yes, sir.
Yeah. So now for a real condition, right? The problem is all we do is we find out rotary beam test for endurance limits, right? This is what we do in most cases. In most cases, this is what we do, right? So in most cases, what we do is we find out a rotary beam test endurance limit. Now this is an idealized condition, right? Idealized condition. So I have to figure out a way to make it work for my design conditions, right? To make it work for my design conditions. So basically, let me give you an example here. Sorry. Yes. So let's take a case. All I have the data is for this kind of a configuration, right? For a RR move rotating beam test. But my product can be anything, right? My product can be a shaft. It can be an axle. It can be rotating axle. It can be a stationary beam. It can be a bracket like this. It can be a bracket like this. It can be a bracket like this. But can I use the same things for what I have gotten the data? The data I have gotten for a nice rotating beam test. But I cannot use that data for real life designs, right? For real life designs, I'll have to make some modifications. And those modifications are called, you have to use some modifiers. So those modifiers, then give me a minute, let me see. So these modifiers, if you talk about, so these modifiers can be various things. So these modifiers can be something called, first modifier is surface condition. How is my surface? So my surface can be machined, right? It can be ground. I can grind and you can get a ground surface. I can have forged surface. I can have various machining processes, make that thing, right? And each will have an effect on your fatigue life. So the first thing is what kind of surface condition I have. So I have to modify for this surface condition, which is called Ka. The second is size modification factor. What is the real size? Because when I do this rotating beam test, it has a size, some sort of a specific geometry it has. But in real life, my product can be, say, 20 inches thick, 20 inches shaft or 2 inches shaft. Can I use the same data for designing both 2-inch shaft and 20-inch shaft? Can I do that? Can somebody answer this question in your this thing, in your chat box? Can we do that? Can you use the same fatigue life equation, so to say, for a 20-inch beam and 2-inch beam, or 20-inch shaft, 2-inch shaft? Is that doable? If yes, why yes? If no, why no? You can either use your chat box to say, or you can use unmute yourself and talk to me. Yes, it's a very correct answer, Srijan. That depends on radius or so radius, length. If length also, if it is a say some sort of a cantilever. But why is it dependent on radius and length? That's the fundamental question. What changes if you change the dimensions? What changes if I have a different dimension? What changes? So basically, say if I apply same, for the lack of better word, if I apply same, say, same in bending, same curvature in both. So my curvature or bending radius is same in a small one and in a big one. In a small thing and a big thing, same curvature I am saying, or same bending radius I am making. What would happen in a big in a thicker beam if I am bending a beam and a I would say a smaller thickness beam. So higher thickness is smaller thickness beam. If I am bending it to say same curvature. So stress concentration is not the right word here. Stress values will be different because strain values are different. I'll derive it for you as I go there, but it's a very correct answer. So stresses will be different. Now, if the stresses will be different, your fatigue life has to be modified accordingly, right? So there is a modification factor which you will have to use, and it's called a size modification factor. So you'll have to use a size modification factor. Now, loading conditions, whether it is bending or torsion or a combination of bending and torsion, you have to account for that, bending plus torsion. You have to account for what kind of loads you're applying. Now, if my product which I am designing runs at higher temperature, what happens at higher temperature? Why should I correct for temperature? So if I'm using a device at higher temperature or a component at higher temperature, what does higher temperature do? Creep is one thing. Melting, you don't use a component near melting temperature. You don't do that. You will actually operate it at much lower temperatures than melting temperature. So it's a very good answer. Material properties changes. Typically what happens is material softens. So material is more ductile, right? So at higher temperature, the chances of brittle failure reduces. So actually you can get better fatigue properties because now it won't fail in a brittle mode. So that also needs to be accounted for, the temperature modification factor. Then there is reliability, right? I want the thing to be reliable. There are a lot of these parameters, right? Which I'm using. I'm accounting for it, but some of the parameters I'm not accounting for it, right? If I want reliability, so I will do some sort of over design to account for any uncertainty in my calculations. So I'll put a fudge factor which will forcefully over design. So basically what I will do is if I'm using it at 10 kpsi, I'll design for 40 kpsi, assuming that some of the things which I have not accounted for will be accounted for and it will be more reliable, right? And then there is kf, which is other modification factors, right? So basically for the part is SE, for the idealize is SE dash. So that is the terminology, SE dash and SE. So I can get for an actual part, functional part, I can get SE by adding some of these modifiers, Ka, Kb, Kc, Kd, Ke, and Kf on the ideal value of ideal endurance value. So this is what I wanted to give you some preamble to what I'm going to do today, and we'll cover each of these one by one. Okay, that's what we will do today. This, yeah. So this we have already discussed. So typically what happens is for ferrous materials whose ultimate strength is less than 200 kpsi, rule of thumb is 0.5 SUT. I showed this here also. If you see 0.5 UST is this one right here, right? If it is greater than 200 kpsi, you do 100 kpsi, or 700 MPa is same thing. It's actually same data. If it is greater than 1400 MPa, we design it for 700 MPa. That's a rule of thumb kind of a thing. Okay, so these are the first order approximations for SE dash. first order approximations. These are first order approximations for first order approximations. For ideal endurance limit. Ideal endurance limit. For carbon steels. Now, which I talked about surface modifier. So surface modifier, people have done a lot of experiments. So a lot of this is empirical. People have done a lot of experiments and fitted the surface modifier, which is a function A S U T raised to B. This kind of a thing. And people have found it for various materials. For ground, it is 1.34, or in MPa, if you know SUT in MPa, you should be able to find out what would be the A and B for ground for different SUTs. So people have done a lot of tests and fitted data. So these are the data fitment actually. So you have a lot of experimental data and you have fitted empirical relations to it. Very much like what you do today all with data sciences. That's what it is. It's just a crude way of fitting. So you just fit power laws to the data which you have. Fairly, and it works fairly well. So I'll show you some of these for different conditions. Let me just go ahead and reshare. I'll unshare it and I'll share my this thing. Just 1 second, let me unshare it. Okay, let me unshare it in a minute and then I'll go ahead and okay. So I'll share it again here. Now you can probably see the screen. So basically, we have this, right? This is what we were saying that this is there. So if I have for ground, if I have 1.58 and 0.085, let me find it for a 400 MPa steel just 400 MPa. Let me just go ahead and do that. So assuming that I have 1.58, 0.85 for a ground surface, this Ka turns out to be 0.95. See, for the so ground surface, the Ka is very high, 0.95. Let me just show. So ground surface is 0.95. Let's see machining. So machining, the parameter is machining and cold drawn have the same parameter. So you have about 4.51 and exponent is 0.265. Let's find out what you get with this one. I'll just keep it open here and I will just, yeah. So now I have what is 0.451. A is 4.51, and B is 0.265. 0.265. And let me just find out what will be my shift enter and then this. This should be 0.92. So for machining, I have 0.92. Machining, I have 0.92. Let's go see hot rolled. Let me see if it's hot rolled 57.7. A is 57.7. 57.7 and 0.718 minus 0.718. 718. It is 0.78 K. So K keeps on, for smoother surfaces, K is high. For rougher surfaces, K would be low. Let's see for asphalt. Asphalt should be the lowest, I believe. Let's see what it turns out to be. 272, 0.995. 0.995. So 70.70, right? So basically ground is the most smooth. So it has high K value, and as forged would have scales and everything. As forged has a very rough surface because it's actually a, especially if you do hot forging, there will be scales and the like. So it will not be a very smooth surface. So that's why you have this modifier. And why do you think the surface roughness will affect this fatigue life? Any answers here? Why should this be the case? Any suggestions? Why should surface roughness actually affect this fatigue life? What happens if rougher surface is there? Any suggestions? Micro cracks, yes. So there can be surface cracks, and the rougher the surface, the larger the cracks, and they're very close to the surface. So it can progress, right? So surface can progress, and surface cracks are exposed to the highest value of stresses and strains. So in a nutshell, what will happen is this can be crack initiators in some form. So the smoother the surface, the higher the fatigue life. So I'll give you, and you can look at some of the surfaces also. If you see, these are some bearing surfaces which I actually worked on, trying to characterize the functional response of it. So this is what some of the surfaces which people use in bearing: ground, honed. There's some process called hard turned. Hard turned basically means that people actually harden the steel and then turn it with a cubic boron nitride tool, with a very rigid tool, so that you actually get a very smooth surface. As turned surface is very smooth, almost like a finished surface. So you don't do a secondary grinding. So these surfaces, you see that they have inherently different surface profiles. And IF is actually vibratory polishing. So it's polishing. You take loose abrasive and polish it. Honed is basically what happens is you have a cross-hatched structure, meaning that there are two stones. So engine cylinder is always honed because it can store bearing, it can store lubricant in those cross-honed structure. So for different functions, you will have different surfaces, but each surface will have a different surface profile. And as you said that it can be, if the surface is rougher, it can be precursor to a crack. Okay, so you have to account for this in fatigue life when you design your fatigue life. Okay, so that's the first one. So what I will do is I'll stop sharing this and go back to the other one. Okay. Now comes very interesting concept. Size factor, right? So this is what we discussed. So let me tell you, like if I have something like this is what I was telling you, why size factor is important. Let's say I'm doing a beam bending. Something is wrong. It's not recognizing my pen. Okay, I have some room here. I'll draw it here. So basically what happens is, if I have to see strain, how do I get strain in bending? So this is say neutral axis. neutral axis, which is unstrained, right? Neutral axis doesn't have any strains. It actually remains unchanged. This is the top fiber, which is under compression. Bottom fiber is under tension. Now, if I have to find out at any location Y from the neutral axis, what will be the strains? So basically, if I assume that this is total angle is theta, so I can find out the strain would be the initial thing, which is rho theta, and rho is the radius at neutral axis. So rho theta was the initial one. So basically, so the final one is rho minus y theta minus rho theta divided by rho theta is delta L by L, or strain. So strain will basically become minus y by rho is strain. And your stress is E epsilon. Right? What this basically means, for same, if I have same curvature, a larger beam and a smaller beam, right? So y will be much larger, right? Say if I have a 2-inch beam which is bending and a 20 each which is bending, my y can be 10 times, right? For same curvature. So I have to account for this. I have to account for this size. Because my strains are higher, my stresses will also be higher. So this is for bending. Now let's take torsion also is similar. Torsion will also have a similar effect. So if I do torsion, then what happens is, sorry, did something here. Oh, just 1 second. So let's see torsion, what happens. So in torsion, what will happen is, at every location, there will be twisting. It will twist. So if I know angle of twist, say at this location, this is L, my twist angle is say phi. So my strain will be, shear strain will be rho phi by L, which is gamma delta y by delta x, tan gamma. So this is what happens in torsion. Same thing will happen in torsion also, right? In torsion also, what will happen is the larger is rho, the higher is the strain. Larger rho means higher strain. Higher strain, and stress will be G gamma. So if my gamma is higher, so this also I need to be accounted for, right? Both in bending and torsion, or a combination. So I'll have to take care of something called size factor. And this is how you do the size factor. The likelihood of crack initiation is higher because higher stress. And these are, again, people have done these tests and found out, fitted this data. So a lot of this design which people do, right, is driven by experiments. People have done experiments, fitted a lot of data, and now they use this data for design. So whatever today people talk about data-driven models and all this, design has been using it for centuries. Okay, they have created a huge amount of database which they use for designs. And some of it is physics-based, but a lot of it is that you have something called phenomenological thing. We know that there is some scientific dependence, and based on those factors which are relevant, you fit data. Okay, so if it is between 0.1 to 2 inch, this is the equation. If it is between 2 to 10 inches, you have this equation. So you have all these KB parameters, and this is only for bending and torsion. If it is just axial load, then we don't have any correction factor. No size factor is required. It's only for bending and torsion, or combination of this. Okay. Any questions? Okay. If none, I'll move to something else. Then there is load factor. So accounts for changes in inertial limit with different types of fatigue loading. So combination, you have to do something differently. But for bending, they use 1. For axial, 0.85. For torsion, 0.59. So this is how you use this load factor Kc. Okay. So I'll have to use this Se. I'll also have Kc. And these are all multiplicative factors, right? You keep on multiplying Ka times Kb times Kc. These are all multiplicative factors. There is a temperature factor also. At lower temperatures, brittle fracture is high. At higher temperature. So if you see at lower temperature, St by SRT, room temperature, and the high temperature is 0.1. But if I go at 1100 degree Fahrenheit, the St by SRT is only 0.567. So what happens is my stresses, failure stresses, or my yield goes down drastically. My yield goes down drastically. Goes down drastically. It's easy to deform. So this factor also needs to be accounted for, temperature factor. So when you design your anything, right, you have to take into account all these conditions. At what temperature I'm operating my machinery, at what loading conditions I'm operating my machinery, what is the size factor, and accordingly, you define your actual design SE based on accounting for all this. So whenever you choose your operational stress, especially when there is a dynamic loading, you will have to figure out how to choose the correct endurance strength. Okay. Then what we do is go to the next factor, which is reliability factor. Now, reliability factor is again a very nice, sweet thing. If I want roll reliability of 50%, I just use Ke. So whatever I do, my Ke is just 1. It is not. You don't need to include. If you want row reliability, 50% reliability, whatever I have find out, this is fine. So if I use 0.5 SUT, 50% of the times you should be okay. Right. So, but if I want to be have 99.99% times I want to be okay, I have to do it 0.620. So depending upon what kind of reliability you want, how critical is the application, right? If it is an application, it is not very critical, right? If it's a pulley of for a simple application where failure will not have a big consequence, I design it with K is equal to 1. But there is a condition where failure can be life-threatening, right? So I have to use my judgment and over-design it. Okay. So I have to take a call. If I'm using it for aerospace component, I will be very cautious. If I'm using it for, say, a normal application, maybe a screwdriver or a wrench, it's okay if it fails. Right? A screwdriver breaks, big deal. Right? But if an axle fails, it's a big deal. Okay. So you have to take that call on what kind of application is there, and based on that, you have to design your product to be reliable. Okay. And the increased reliability, you can use this KE factor, starting from 1 to 0.6. Okay. Now there are miscellaneous effects. These are ones which just go into if I have to consider if there is residual stress, if there's a tensile residual stress in my system, the fatigue life will be compromised significantly. So I have to account for that. If there's a directional courtesy from cold working, if I'm doing cold working, then what happens is some conditions. So the direction in one direction, the direction of deformation will be very strong. Other direction it will have an isotropy, especially if I am doing rolling kind of operation. Roll sheets have higher strength in the direction of deformation, and they have lower strength. So this has to be accounted for. If I'm doing case hardening, sorry, let me go back. If I'm doing case hardening, if it's a corrosion thing, if it's a surface conditioning, cyclic frequency, fretage corrosion. So for all this, I'll have to have additional factor of safety because it can corrode, right? There can be fretage. So for all this, I'll have to account for in my design. And this will require some research and testing to make your data more reliable. Okay, so this is what I wanted you to get some idea of how do you, yeah, 1 second, somebody has a question, let me just look at it. What is fretage? Anybody knows what is fretage? And then I'll answer what fretage is. Has anybody heard the word fretting? Fretting failure. So it is like if you have, I don't know, I can say it in Hindi. When you have this papdi nikal jati hai na, what do you call it? How do you express that? When you have this kind of delamination kind of a thing, surface delamination or something, almost like papdi. It's one layer.
Okay, sir.
So that will be a fretage kind of phenomenon. Okay. So all this has to be accounted for. These are some critical applications where you may have corrosion. I'm designing it for marine application, right? So I'll have to have an additional factor for making sure that corrosion doesn't happen. Okay. Sounds good. So we'll move to the next thing. Now, typically what happens is I will never have fully cyclical stresses, right? I'll never have something like this, where sigma m is equal to 0. And I have like sigma a in. So I will never have an ideal fully reversed condition. Ideal reversible stress will not be there. I will have something like this. I'm showing you here. I'll have something like this, right? With some, so there are some small changes here, right? I can have where sigma m is not equal to 0, and it's a general fluctuating. I can have something like this, or I can have some very it is still some sort of periodic, but your amplitudes are varying as a function of time. So there is a function of time, but amplitude is not constant. So here it is repeated, right? So sigma a is same, and here it is completely reversed. So this is what we have been doing up till now. But there can be these 5 conditions also, right? And what I do is all my tests are done for this. So how do I characterize any stress? What is your suggestion? If I have to characterize the fluctuating stress, how should I go about characterizing that stress? What should I do? Any suggestions? Think about it and come with some suggestions. At least one should be there, right? Nobody is giving me any suggestion. Some suggestion I need from you guys. I can have any of these 5 conditions, right? Where my sigma m is non-zero, where sigma a1, sigma a2 are different, right? Where it's function of time. All sorts of things can there, right? Where there is small ripples. I can have any loading. So how do I first characterize a signal? If I had to characterize time dependent stress, what should I do? How should I have a method for doing it for all? Superposition with Fourier series. Okay, let's not go that mathematical, right? Most of the engineers on field would not have a Fourier transform thing, and Fourier transform is typically important if you want to know frequency component of it, which frequency the power is there. This is a good one. I like it. Average and deviation of stress. Very good idea. That's a good idea. So what I need to do is I would need some sort of a amplitude measure and some sort of a mean measure. Right. That's a very good analogy. Very close. So I need some effective amplitude value and some mean value. So the way I will go and do it is I will show you how to do it. I know my sigma for any signal, right? For any, let's not say signal, for any time dependent stress. If I have a time dependent stress, right? So I will have minimum and maximum values I can find out from the time signal. I can find out minimum maximum. I can find out two things, which is one is amplitude component, which is defined by sigma max minus sigma min by 2, which is what he suggested as deviation, something like that, right? This will be sigma amplitude, and then there will be a mid-range component or average component, which will be sigma max plus sigma min by 2. So this will be mid-range component. This will be, so for any signal I can find out sigma A and sigma M. Okay, for any kind of fluctuating signal. With this information, I will use this information to now do it for any loading. So now equipped with this kind of formulation, I can find out relationships, the fatigue life or endurance limit for any signal which is not reversible. And then there is something called stress ratio, which is sigma. Sorry, let me go back. Sigma min by sigma max, and amplitude ratio, which is sigma A by sigma M. So these are the things which you will use: sigma A, sigma M, R, and amplitude ratio A. So let me just show you the important things. These two are important. These two are important. That's how we characterize a fluctuating stress, with these parameters. Now, there is another thing. What happens if there is a stress raiser? What if there is a notch? Or what if there is a change in the dimension, very sharp change in the dimension, where there are stress raisers? So I will need, along with these parameters, sigma FO and sigma MO are parameters for sigma AO and sigma MO are for normal beam, right? For rotating beam, these are the parameters. But if there is a stress concentration, I have to account for it, and I have to find out what will be the stress concentration ratio. And this stress concentration ratio is given by this. If my Kf max by sigma max is less than Sy, then this, and if Kf is less than sigma y, you use this kind of a formulation. So in a nutshell, what this basically means is that if there is a stress raiser, or there is a fluctuating load at stress concentration, you have to account for that. You cannot just use sigma A and sigma M. If there's a stress concentration, I will need to have another factor which will amplify this, because if I have a stress raiser, right, normal sigma A and sigma M will not work, right? They have to be amplified. So this is an amplification factor which takes into account presence of a stress concentration. Okay, so this is how you decide KMF is equal to KF, and these you can look up in the table. So these are there which you can look up in the tables and find out what will be. And typically it is applied to the alternating stresses, sigma A. Okay. And this is the factor, and you have to look in the table to find out what will be these factors. So when you do problems, you'll be able to find it out. I'm just giving right now. I'm just laying it out for you. When you do problems, you can learn how to account for these stresses. How do you go ahead and learn about fatigue for different loading conditions? So I know sigma m and sigma a I can now find out for any fluctuating stresses. So how do I get the real data now? So this is what we will do a little bit today, and then next Monday, because the coming Thursday we'll have the quiz. Next Monday we'll solve some problems for real conditions. So today I'll just prime you with some ideas about how to do that. So the one thing is doing mid-range on abscissa and sigma m on one, sigma a on the other. Right, something like this. So this is sigma m and this is sigma a. We plot it. Now let's do a thought experiment. If my sigma a is equal to 0, what does it mean? If sigma a is equal to 0, what does it mean? Sigma max is equal to sigma min. What does it mean? Not contact stress, but it's just a constant stress. Yes, sorry. I read contact. Sorry, constant stress. Very good. It's a constant stress, right? So what will happen if I use a constant stress? What will happen if I am below? So if I am on this line on x-axis and I am applying constant stress, it's not a fluctuating anymore, right? If sigma a is equal to 0, means it's not fluctuating stress anymore, right? So where will it, if I apply constant stress, where do you think failure will occur? What will happen? It will yield at y and it will fail or fracture at ultimate, right? That's what will happen if I do this. Now do another thought experiment. If my sigma m is equal to 0 and sigma a is there, sigma meaning it is a completely reversible cycle. What happens in completely reversible cycle? If I go on this line, what will happen? I know that if I go for a cycle at 10 to the power 6 cycle or some cycle, it would have an endurance limit. It will fail in endurance, right? And so endurance will come first. SE is much lower, especially at higher loading cycles. At larger cycles, it's at smaller number of cycles, you may have higher yield. But if I plot something like this, these are the two conditions. So basically, what you do is you do this. First thing is you plot SY on both conditions. This is called a Langer line. This is the Langer line. Then you plot SUT here and SY here. And for any condition sigma, for any combination of sigma A and sigma Y, if I am here, I have it will fail here. So the failure is for this sigma A and sigma M combination. So if there is sigma A and sigma M, you will have, this will be your failure limit, failure point. Okay, so this is your failure envelope right here. So what will happen is here between this to this place, between this to this, let me just go ahead and erase this. So this to this combination, if I have this combination between this and this, it will be fracture before yield. But if my sigma m, if my sigma a is very low, it will yield first. So this is fracture locus and this is yield locus. Here in this combination, if I have very high value of sigma m, and low value of sigma a, yielding will occur. If its converse is true, then fracture will occur. Okay, then it will fail in fatigue fracture. Here it will fail in yielding. So that's what happens typically. So you basically keep on plotting sigma m and sigma a, and you will be able to find out what will be the. So this is something called a modified Goodman diagram. This is one way to estimate failure. And all it is it's a plot between sigma a and sigma m. Modified Goodman line, it's actually SE, endurance limit to ultimate, one line, the other line is yield, and then you basically have a limiting boundary. So this is the limiting boundary. So the limiting boundary is this. If you want to understand, the limiting boundary is this. From here to, sorry, let me go back. From here to here it is this, from here to here it is this. So this is your boundary. Okay. Right? Any questions here? So that's one way to do it. I'll show you how do you do it for real problem. That we will do in the next class. But today I just want to give you some idea of how do you go ahead and have these calculations. What are out there? The second one is abscissa represents the ratio of mid SM and ultimate strength with tension plotted to the right and compression to the left. Let me go ahead and show you this. So this is what is the other way to plot. So here what you do is you plot on x-axis is SM by SUT. Okay. Mid-range strength by ultimate for both compression and tension. Right. And this is SA by SE dash. So amplitude SA by SE dash is which is your endurance. So alternating by endurance and mean by SUT. So you see that here in the tension, it keeps on decreasing because tension failure happens. Compression, you see, it's almost constant. So compression, if you see the effect of this alternating is much more pronounced in tension as opposed to compression, because compression the fatigue life is still reasonably high. If you see SA by SE dash in tension, you have much faster. So if you have higher SUT, your SA by SE is much lower. Okay. So this is what, and here it's almost constant. This SA by SE dash is almost constant. Okay. So high. So if I have this SM by SUT higher, this value, if I have higher, this value keeps on decreasing. So SM by SUT. So if I have higher mean stress, then this will mid-range stress. This SA over SE dash would be lower. Okay. So in a nutshell, SA plus SM somehow remains. This is a combination which we saw in the previous thing, right? It's a combination of SA and SM. How the fatigue will happen. So basically, SA and SM both have an effect on your fatigue. So this is where the failure will occur, which is a function of both SA and SM. But it's more pronounced in tension. In compression, you see it to be a fairly straight line. So you don't see a lot of effect in compression. Okay. Okay. Now there are other methods also. So first one I saw was Langer line, which is yield, just yield connecting yield, sigma m and sigma a. We discussed about something called modified Goodman, which is this SE and SUT. Then there is SE and SY, which is Soderberg. Soderberg is very conservative. So Soderberg is very conservative because it doesn't even go to U2, it just goes to Y. So Soderberg is there, modified Goodman is there. And then there are two other non-linear lines. One is called ASME elliptic and the other one is called Gerber line. Gerber line. So in essence, what you will see is Gerber line is the most liberal and the most stringent is Soderberg. Okay. Because this Gerber line is based on data. So this is more accurate. So this is Gerber line, this one. This is the least conservative. And the simplest one, which is Soderberg, is the most conservative. So if you use the simpler model, you are over designing. And ASME elliptic passes to the data, but also does yielding check. So it has both yielding criteria, like your Soderberg also looks at yielding, and both Goodman also looks at yielding. But your Gerber is just best fit. It doesn't look at any yielding information. Okay, so these are some of the 5 things. There is, we'll do problems for everything. There is modified Goodman, there is ASME elliptic, there is Soderberg, and there is Gerber. So these are the 4 key things. Langer is actually just for yielding, but happens to be a criteria for failure. Okay, so these are the things which we have. I will solve it in the next class. We'll take each criteria and show you how to use that. So you'll get something like this. You will actually get a factor of safety for every condition. So whether for a given condition it is safe or not, we find out, or design is safe or not. And the safe design comes from your factor of safety. How much factor of safety it is there. For what I can do is I can actually show you. This is how it works. So basically, if I have something like this, if I am here, right? If my combination of SA and SM, this SA and SM is here. So basically, this is my factor of safety. This line AA dash and AB dash. So AA dash by AB dash is my factor of safety. Graphically, there are equations I can find it for that. So when I'm designing, if I'm here, if my SA and SM combination, are here, I have failed. So I have to always, my SA and SM combinations should always be lower than these 2 lines, this line and this line. If my SA and SM combination is here, I have failed. Although I'm not failing in fracture, but I'm not failing in fatigue. I'm not failing in fatigue, but I'm failing in just yielding. It is yielding before fatigue failure. Here, from here to here, I will always fail in fatigue. So any combination of this is failed, this combination of SA1 and SM1 is failure, this combination of SA2 and SM2 is failure, this combination is safe, SA3 and SM3. So anything which I am below this line, I'm safe. So I have, I'll plot this information, I'll get this information for given condition, these conditions, and these will come from this data will come from my rotating beam experiments. And based on that data, I can use this information for different SA1, SA2, but these SA1 and SA2 will have to, and then I have to get this SE with the modifying factors, SE with K, KB, KC, SE dash. So this what we plot here, SE, is a is the actual endurance limit with the modifiers for my given condition. So this is how I plot. But this information actually comes from this SC, SUT all comes from my rotating beam experiments. Okay. And based on that, I can predict for any SA and SM combination, any SA SM combination. And these SA and SM combinations are derived from fluctuating stresses. So sigma max plus sigma min by 2 is SM mid-range, and sigma alternating is sigma max minus sigma min by 2. Okay, I'll stop here. And then we'll do the problems next semester, next class, so that you will have fair bit of idea what needs to be done. Any questions now? I'll just take questions for 5-10 minutes and then we'll quit. So this is enough for today. So if you have any questions, fire away. So if I keep a sigma A and sigma M same, where will the failure occur? So it depends, right? Sigma A and sigma M same can be, this is 45-degree line. This is 45-degree line. So it is safe here. It is safe here. It is safe here till I hit this. You get my answer? So sigma A and sigma M is same till my sigma A and sigma M hit this line. I'm okay.
No, sir. My question is, if I keep the sigma and sigma M same, will the failure for any type of loading keeping them same occur similarly?
No, so this is how it will go. If your sigma A and sigma M are same, right? You'll go at 45-degree. In this line.
No. I don't mean sigma A equal to sigma M, but suppose they are different values and I keep them same. So they are not unique for a type of loading, right?
It will always be sigma A is equal to sigma M. It will 45-degree line.
Sir, actually, my question is, so sigma and sigma M are not unique for a type of loading, right?
No. So any sigma A, sigma M combination, that's why I showed you, right? So I showed you this is one. Sigma A1 and it's a different loading condition, right? Sigma A and sigma 1. This is a different loading condition, sigma A2 and sigma M2, right? It may not be unique, right? I can get sigma A and sigma M by various conditions.
But if I keep sigma A and sigma M at the same value, I mean, they're not equal, but if I for the same sigma and sigma M values, I can have multiple types of loading, right?
Yes. So you can have multiple signals which can give you sigma A and sigma M, right?
Yeah, exactly.
Doesn't matter. It will still give you, it will give you a good approximation. This will give you a good approximation because you are designing for extreme condition, right? Sigma min minus sigma max. So that is the worst condition. So you're safe. You're safe, right? Because you're taking the bounds. It may so happen that sigma min and sigma max actually go only for a brief while. In some cases, it goes for many times. So it may so happen that you're over designing in one condition where sigma min and max are reached only once a while. But it will be safe. Safety will not be compromised. I may end up over designing it. I got your thing. What you're saying is, in some cases, if I say I have a fluctuating signal like this, so I'm here, but in one off case I go there, right? So I'm designing for extreme condition. It happens only once a while in this condition, sigma. And in one case, I have something signal like this. Both are not same, right? Here it's happening once a while. Here it's happening frequently. So here I'm over designing it, but it's okay. I'm safe in both conditions.
Okay.
Any other condition? Any other questions? Still have a few more minutes, 2, 3, 4 minutes. Let's discuss something. If you have any questions about the quizzes or the homework assignments, anything? Project? You can ask right now. None? Nothing, no questions about quizzes, projects, nothing?
Sir, in the homework, I had just one doubt. In question 2, in which we had to derive material indices, Is the objective to minimize mass or to maximize the stiffness? It's not really clear from the statement.
The thing is, whatever you have decided there, right? Just write it. This is what I have used. That should be fine. If the question is not very clear, but let me just look at the homework, and then I will. Yes. Homework 2. Okay. So what is it that you're saying here? Where do you want me to look at it?
The second question only, deriving the material indices. It's minimizing for those.
Highest strength and stiffness at the lowest. So yeah. So what I want is two different conditions.
Okay.
Strength to mass and stiffness to mass, both.
And this is while minimizing mass, right?
Yes, for both conditions, strength to mass and stiffness to mass, both.
Okay.
Basically,
Sure.
E by rho and your whatever stiff. The other one is whatever sigma by rho. Some fraction of that. Some indices will be there, right? Like I showed you, right? How your sigma by rho varies for bending, for panel bending, for beam bending. Same thing I wanted. Both conditions, E by rho and sigma by rho. Things.
Okay. So also, what's the weightage for the quiz?
Weightage for the quiz, I don't know yet what I will do because I have something planned. I actually have put everything everything is already there. Let me just see what I had proposed initially. I had proposed this. I had proposed this. I think this is the thing. Assignment for quiz is 30%. So I will try to have a split between this. Once I have it, I'll announce it because I don't know how many assignments I'll be able to give. Right? I would give probably 4 assignments. Each assignment will have equal weightage, give or take. If the assignment has like somewhere it's 40, somewhere it's 50. So that way I would try to have assignments. I try to keep it very similar. Like this homework 2 has what? 5 questions, right? 4 questions. So it will be 40. Homework 1 had how many questions? Let me go ahead and check. Homework 1 had.
We have given maximum marks as 40, sir. Homework.
Okay, so we'll try to keep everything 40. Okay. So each homework will have same weightage. Now quiz, so I have 4 homeworks and 2 quizzes. So we'll split evenly between 4 and 2. Okay. That's what I plan right now. 4 assignments and 2 quizzes is what I want to plan. So your 30% will be divided by that 6 things. I'm not giving more weightage to quiz, especially because it's a remote thing, right? If it's an in-class quiz, I usually give more weightage to the quiz. But in this condition, I'm giving both homework and quiz same weightage. Okay, there will be 6 of those. So each thing should be roughly, say, 5% each. So each quiz and each homework is 5% of your credit.
Thank you, sir.
Any other question? So if not, I will stop this, and Thursday we'll have. Yeah, go ahead.
Will we have a midsem?
I would like to have a midsem because there's a midsem week, I believe, right? In the academic calendar, is there a midsem week for us?
Yes, sir.
So I'll have to figure out how to do that. Maybe similar to a quiz, I'll try to have something like that. I don't know how do I conduct it with because I don't want a very large grade for mid-sem. I don't know what I have proposed here, but this I may change, because what I have proposed here is roughly 30% for exams. I don't know how I'll be able to do exams, but this I can reduce and I can put it into project. I can make 50% and assignments with 40% and exams 10% or something. That I will see depending upon how I can run the quiz, how I can run the midsem. I don't know yet. I don't have any idea how I'm going to do midsem, but we will have a midsem. It may have less weightage than what I have proposed, because I did not know how do we make sure that we can conduct the midsem effectively. Okay. Quizzes still I will try to have because I keep very small time frame, so quizzes also is fine. But midsem I don't want to have a make or mar exam. That is my fundamental thing. I don't want very high stakes exams in this situation. Edit submission option for the assignment. Will it be regarded? What is edit submission option for the assignment? Can you explain that to me?
So basically, in the assignment submission option of Moodle, there is after the grading has been done, there is an edit submission option available. So will the assignment be regraded once the submission is edited or something like that?
So I will give this option only for people who are struggling. If they are struggling and if I feel that they may not be able to get good grades, I'll give that option to people. But usually I would avoid it if you are doing well. So if you feel that you need this exercises option, contact me. Okay. If you feel that, but then there would be only limit 10% or 15% improvement. I'll put a breaker there. So if you're struggling, then you can use this thing to take another shot. So I'll try to use this only for people who say that they are not doing too well, so they want to have take another shot. We'll figure it out. But right now it will only be limited to people who are struggling. Yeah, I don't want to use it for everybody, because most of the people I saw have done well in the homework one. So I don't see any use as of now, but we'll see. I also don't know how to grade in this situation. I'll try to have a very liberal grading policy. That much I can tell you. But then it's a challenge for me also how to make it fair and reasonable.
Okay. Okay, sir.
So we'll meet on Thursday. Look out in the Moodle for the quiz. By 1:30, I'll post the quiz, and then by 3 o'clock, all of you have to upload it in the Moodle. Okay, so that's the plan for the quiz. This is just a test. Don't panic if there are any issues. Just shoot me an email and a message in the chat box. If that doesn't work, I will actually give you my cell phone number. Don't make prank calls on that, but use it for texting in case there is a problem. Okay. If you have nothing, if your power goes off, your computer goes off, everything conks off, use it as a last resort. Okay. So bye-bye, and we'll meet on Thursday.
Sir, can you stop the recording before?